afternoon, Shanika. Daily quiz is up.
I thought you forgot me.
No, I just run a little bit behind. First of a Friday. It is 3:03. So I'm gonna lock answers in 5 seconds. 3, 2, 1. Locking answers. Now. So, what is the order of the element 3 in this group? How many times do I need to add 3 to itself to get the multiple of 4? Essentially, I'm going to have this question, right? So if I add 3 twice, it gives me 9. 4, add 3 again. I get 12.
306.
Oh yeah, 3 and 3 is 6, 3 and 9. 4. Yeah, 3 to 4 could be 12. So I add 3 or 3 times 4, or add 3 to itself 4 times to get my first multiple of 4. Which is then going to be 0. My identity element for the group. So the order of the element 3 is 4. I did not know that. Lucky guesses, or we'll get a 3 out of 3. All right, what question do I got? Sounds like Melissa wants to ask a question.
I went back over the notes and like I couldn't remember what the thing meant again.
Cyclic group.
Yeah.
Cyclic group.
So is that like the element to some power and then those?
What's the photo show? On the wrong screen. So if it's a cyclic group, that means everything inside of the group can be rewritten as a single element to an generator, which would be called a generator. Yeah. So the example was in V6, for that modular addition, we found out that 5 was a generator. Because each of those elements in there, 0, 1, 2, 3, 4, 5, even 5, which is simple, right? I can rewrite as 5 to some powers. We saw, okay, well, obviously 5 to 0 powers will give me my identity. That's what we said. 5 to first power gives me 5. We saw 5 to second power gives me 4. 5 to third power is 3. 5 to fourth power gives me 2. 5 to the fifth power gives me 1. Now I came back all the way around, 5 and 6 power back to identity. We just kept this process going over and over again. We'll see, we just keep getting that, those numbers 5, 4, 3, 2, 1, 0, 5, 4, 3, 2, 1, 0, 5, 4, 3, 2, 0, which are all just elements of these sets. We could change our perspective instead of saying, okay, well, instead of looking at these as those elements 0 through 5, I can look at these as elements of 5 to a particular power. But was it just 5 was the only generator that we could choose? Was 4 a generator? No. Was 3 a generator? Nope. But there was one other one, which was 1, because we kind of saw GCD, or the reason why is GCD of whatever that subscript is n, how many the first non-negative positive or non-negative integers at once. The GCD of that element and that number is 1, they have no generator. That's what we're going to get to today. What makes that true? So I want to prove one other thing first, and this is kind of like what we saw. It's just that even though this is more of just an ad hoc, I'm not ad hoc. We defined our cyclic group to be saying take an element, or so this set that is generated by a particular element A, you're just always going to say, okay, I take A and raise it to some power, but what are my options for all the powers? All integers, right? So I can choose 0, 1, 2, all the way up to as high as I ever want to go, and then farther, and then -1, -2, and then keep going and close on 1 and then lower. So there's technically an infinite number of options, right? But we saw that once we hit a certain point, we just start seeing elements being repeated. The question is, why? That's what we're going to prove first. We got our theorem. It's going to say let G be a group. And let, I know Carissa is here, but I still know you probably don't like it if I use little a's for a group element. So what letter should I choose?
Okay.
I want to say no to K because I want to use that. So you didn't know that?
Yeah.
I want to use K in my group or something like that. M. All right, let's try it. So I'm not talking about whether or not I have a finite group or infinite group. Not going to worry about selecting my cases there. The first case I'm going to say is if the order of that element that we just chose is infinite, then m to the ith power will be equal to m to the jth power if and only if Those exponents are the same. If the order of my elements is finite. 1, 2, 3, all the way to some natural number, but I can actually get to it if I start counting. Then the set generated by that element A is just going to be equal to the identity elements, that element A squared, A cubed, all the way to A to the n equals 1. And you can also get from that, if we know we have a finite order for an element, A, or not A, so I was going to use A. M to the I power is going to be equal to M to the J power. If and only if n divides that difference, I minus J. I'm really fitting a lot into this one. There's kind of 3 main statements here. First is that this element has infinite order. It just means that if I keep trying to operate with this element by itself, I will never get back to the identity. It keeps creating something new. There's never a point in the identity element to create. Which also is an indication based on our history, we never repeat. So I've never seen an element repeated twice. And because of that, if I never see anything repeated, then I know if I'm taking that particular element and raising it to 2 powers, for those outcomes to be the same, the only option when I have infinite order for this element is that those 2 indices has to be the exact same power that I'm raising. Again, that's not because I never repeat. But if I have finite order for another, then I know what that set generated by that element is going to be. I also know how many elements it's going to have. So it's always going to be either by identity element or A to the 0th power, A to the 1st, A to the 2nd, all the way up to the A and +1, and how many elements will be in that set. An element, which is the order of that particular element. But this means then I'm going to start seeing the repetition, the outcomes when I raise A to some power. So now I can have 2 different I's and J's that end up becoming the same element. So how do I guarantee that they are going to be the same? Well, if those exponents satisfy a certain relationship, order of my element n, that is, n has to divide the difference. But to prove it, it's going to come down to division out. So quick reminder before we get into it, because it's going to be important. If I say the order of that element m is n, then n is the smallest positive integer such that when I operate m with itself n times, I get what element? Identity. That's just our norm. So move that proof down a little bit. All right. I need to start off my preamble. The two things I get to start off with without any assumptions. Let G be a group. And let M be an element of G. All right, let's deal with the first statement we have here. That is, if the order of my element is infinite, then I get this. So this is a what type of statement? If it only I have corrections to show, but it's actually going to be easy. So we're going to let the order of this element be infinite. So if I keep operating M with itself or its inverse with itself, it'll never ever become the identity. And I'm going to have that if and only if statement, I get two directions. The forward direction is going to say, assume that M to the I is equal M to the J. I can make an identity element appear here by multiplying both sides by 1. Technically, I have two options. Inverse of 1. But yes, inverse of 1. So M to the I. We'll multiply both sides by M to the negative I. That's going to give me my identity element is equal to M to J minus I. But M has infinite order. Since M has infinite order, what is the only possible outcome that can make this true for I and J? What's the one thing that we reliably know? I raise it to that power, it gives me the identity. Zero is the only exponent that does it reliably. And since I know M has infinite order, there's no other exponent out there that can do this. This means the only option for J minus I is for it to be what? 0. And if J minus I is equal to 0, what does that mean about I and J? They're equal. We get that first statement. If I go in the reverse direction, well, it's pretty easy. Not really much to do there. If I assume the exponents are the same, then the F power is going to be the same thing as M to J power because we're operating M the same amount of powers. No matter what I and J are. We get that first if and only if statement. But all under this assumption that the order of our element. So what are we going to assume next then?
The order of M is M.
Yeah, so it's finite, but absolutely. So next, we're going to say let the order of our element that we chose equal to N for some natural numbers. Now, which one do you want to tackle first? You want to prove that the set generated by this element, obviously is A. You didn't catch me on that?
I noticed it by that.
Y'all are supposed to be my proofreaders. I'm not responsible for it, right? So let's change that. That's me going back to what I had in my lecture notes. All it is just one little small notation. A's were I originally wrote. But we said choose one instead. So is everyone clear on that? What that changes? Just want to make sure we're on the same page. That made that small. I mean, since I tested you. But still, which one do you want to prove first? Do you want to prove that these two sets are equal? So if I raise m to any power, or any, that power can be any integer, it's the same thing as those n elements. Or you want to prove that if and only if stated first.
The first one.
First one. So we also have a second. We have a second, right? And so if we have finite order, we get these two sets are equal. And m to the I is equal to m to the j, if and only if n divides I minus j. And dot got erased from j. Third, let's say set equality is the perfect choice because that's the next thing I did in my lecture. Where so what happens when you change up A to an M only. Let's keep it simple. We'll show and just to make it nice and clear. That set generated by A, which is again A to B and we stole that from me, A to the peak power, such that B is an integer.
So using m. I see you want to be for something.
Yeah, I always want to use A. That's what I'm used to. But I'll get it right here. Really what we're doing is proving these two sets are equal. No matter if you're raising it to any possible integer, it's going to boil down to one of these n elements that are in this set. So, how do I show two sets are equal? At the beginning of this class, it was technically during our digital week. On your page, you get the screen. And then Dr. Barr done it with you. He's talked a lot about sets. How do you prove two sets are equal?
Yeah.
Prove that they're not.
No, you're not.
They are they not?
That you're not.
Oh, try to do a proof by contradiction. You probably could, if it's a true statement. I'm gonna try. But the easy out idea is that when you go to philosophy of logic, the direct proof is considered more profound and more powerful. So proof by contradiction or proof by contrapositive. So they're logically equivalent, but because you can't use the term as is, you have to reshape your perspective on it. A lot of there's some mathematicians or some philosophers that believe that it is the less proof. Still valid, but less. So yeah, so like we can use directly. If to prove two sets are equal, you just have to show that they're subset. A is a subset of B and B is a subset of A. And A and B have to be equal. Because what does it mean to be a subset? It's within it's within spot, right? Everything from the first set is also an element of the second set. That's what it means to be a subset. So we do it here. We're going to choose first something from this set that is generated by A. Gosh darn it. I shouldn't have let you choose number letter. I should have just said suck it up and be A. No, it's too late now. It's too late now. But at least I caught it this. So I'm just going to be choosing some element from there for some and integers. By the division algorithm, I know there exists a Q and an R in the integers such that A is equal to Q times N plus R. I'm going to ask you a question in a second. So really I'm thinking about dividing N into the value K. So N is my divisor. So when I write this statement of the division algorithm, there exists Q and R such that A is equal to Q times N plus R, with R being greater than or equal to 0 and less than 1. It'd be N, that's in my divisor. So now I go back and I consider M to the Kth power. But because of the division algorithm, how can I rewrite that value K? M to the Q times N plus R. Wait a second. I've got some exponent rule that still work within groups. M to the Q times N plus R, I can split that up into two different multiplications. M times Q to the N times M to the R. Ooh, there's one other clever rewriting I can do. Essentially make that Q to M to the Q times N disappear. Plus, this coming from where? N, the little n, n is the name. What does n represent? So for the capital N with boldface notation, yes. I'm talking about that lowercase n. It was the divisor for the division algorithm, yes, but even before that.
That was the order.
Order of my element n as in Mary. So I know if I take m and raise it to the nth power, because n is my order for m to the nth power would become what? E. There you go. So instead of doing m to the q to the nth power, flip it around. Yeah. Which is just going to give me my identity element to the qth power times m to the rth power, but I take an identity element and multiply it by itself q times, it's still going to be the identity element, and I multiply that by m to the r. I'm left with m to the rth power. Where does m to the r power also exist? Inside of the set. Because r was my remainder for division. What is the possible values I can have for my remainder? 0 to everything less. It's gotta be an integer, which means the highest value you can achieve is the next one. And where all the exponents for my values of m, or exponents for m inside of the set, anything between 0 and -1. So since m to the r power would be in the set, this also tells me m to the k power, because we showed that those two things are going to be the same. It's also in that set. Therefore, if the set generated by that element m has to be a subset of this set right here, m squared all the way to m n minus 1. All the benefits of originality. But I got to show it the other way around. But what do I kind of get for free? It doesn't matter what element that I pick from this set. M squared all the way to n minus 1, these are all just m raised to an integer. Means every single one of those elements is also in one other set. Set generated by n. Because how do we define the set generated by n? That's what we're trying to show. Well, we're almost there. Where did I write it out? Here. It is a set of all elements with like m raised to some integer. And is that not what all of these things in here are? So I know that this is a subset of this. And since they're subsets of each other, what do I now know? Yeah, they're equal. That is kind of like my 2a. That's really the second statement I have there. I'll pause for a second. You know, I had a few m's turn into a's that turn back into m's. What questions do you have?
So. I know we are trying to prove that in price and C, but couldn't you also just be a subset from having vacuum equal?
Absolutely. But we showed their subsets of each other. Well, that's
In both ways.
That's what gives us the equality. Yep. But in general, right? Yeah. You can be strictly one set. One can be strictly a subset of the other. Got it?
What was the oh, never mind. Never mind. Okay, we got it.
Don't know what it is, but I'll accept it as a big. Figure it out for yourself. All right, what's the last statement that I need to prove? I'm back up to my theorem. I've shown if my element has infinite order, then m to the I is equal to m to j, if only if I is equal to j. If it's finite order, we show that these two sets are the same, what's the last and each shell?
The if and only if.
Yeah, that if and only if. Which again gives me two directions. So which direction you want to do first? The forward implication and backward implication? Forward. So we're going to assume that n to the I power is equal to m to the j power, and our goal is to show n divides the difference of those two exponents. Guess what we're going to use again? Division algorithm. So maybe just follow the same assumption. Assume m to the I power is equal to m to the j power. Then I know if I multiply both sides by n to the j or negative j, I'm going to get n to the I minus j would be equal to what element? Mhm. Then the element. By the division algorithm, then we know there is going to exist a Q and R in the integers such that I minus j is equal to Q times n plus R with 0 less than or equal to R n. It's really I'm considering what happens if I divide n into I minus j. Because ideally you would evenly divide, and if that's true, then my remainder should be what? 0. Well, now we have two pieces of information we can work with. If I consider n to the I minus j, it's going to be equal to the identity. And I can also rewrite that I minus j as a multiple of n, which I know is the order of my element, plus some remainder r. So what we now know is that my identity element, which I can rewrite as m to the I minus j, based on our assumption. And by the division algorithm, I can rewrite this as m to what power?
Q N.
Plus r. Wait a second, we already saw this before. I can reduce this down again. Following the same steps, I'm going to end up being left with m to the r. So first, I need to make sure I separate them. Q to the n, or q times n r, equal to n to the n power times q times m to the r. And since n was the n as in Nancy is the order of my element m as in Mary, I get the following. I also know that if I raise m to that remainder power, I also get what particular element? The identity. But now wait a second. I define the order of an element to be the what integer?
Smallest positive.
Smallest positive integer. n should be the smallest positive integer that I can choose. So that when I raise m to that power, I get the identity element. But that remainder that I got there has to be strictly less than its order. What is the only way that I can resolve both of those two facts? If r is 0. Therefore, let's write that out. Since n is the smallest positive integer such that n to the nth power is equal to my identity element. And we know that remainder must be 0. And if I go back to my division algorithm and the remainder is 0, what can I say about n, the difference I minus j?
Zero?
If remainder is 0, yes.
Oh, they equal to each other. So what?
Well, no, I minus j is equal to some integer times n, right? The remainder that our term would go away.
Oh, I could end by.
And divides I minus j. I minus j is a multiple of n. Of the division of. So I minus j is equal to q times n. Therefore, n divides I minus j. And that's the harder one. The reverse implication is actually kind of simple. Because we assume that n divides I minus j, and we know there exists I'll use q in the integers such that I minus j is equal to q times n. So if we consider a to the I minus j power, how can I rewrite that exponent?
Zero.
Not 0. I don't know I is
UA.
equal to j. UA. And I can rewrite that again as, oh, why did I go to A? Test your mental fortitude. That's what it is. You need that on a Friday, right? But we see the same trick again. I can rewrite this as m to its order to the cubed power. That's just going to give me my identity element cubed power, which is just my identity element. So I have m to the I minus j is equal to the identity element. What can I multiply both sides of that equation by? Get my desired result. By m to the j power. See Sanaya's face, and we'll do it all out. M to the I minus j is equal to my identity element. If I multiply this equation on the right on both sides by m to the j, I'll be on the left side, left with what? M to the I. On the right side, if I take the identity element, multiply by j, I'm just left with m to j. The order of the element divides the difference of those two exponents. And their outcomes, and the I is going to be equal to J. And I've now proven all three of my statements. You take a nice deep breath. I'm done. I'm going to quickly write some stuff down. One is a corollary that I think is kind of cool. For any group elements A, we get that the order of the element is going to be the same as the cardinality of the set generated by element A. And that's what we saw when we were talking about the proof. How many elements were in the different color? This set right here. An element, and we assume that the order of the elements was as well. This is a direct consequence of that proof. And hold on tight, so we're going to go through this theorem. I'm going to prove it real quick. It's not going to take that long, or at least only the first part. Let G be a group. And let little a be an element of G. With the order of that element A, B, N. I.e. that it's finite. Let K be a positive integer. Then we're going to get two things. One, the set generated by a to the k power. So if I take a to the k power and multiply it by itself multiple times, this is going to be the same set as the set of all elements of a raised to the GCD of n and k. And the second result, we're not going to prove, then that the order of a to that k power is just n divided by the GCD of n and k. We're going to prove this pretty quickly, just the first sentence. Now let D be the GCD of n and k. And since this D is the greatest common divisor of both n and k, then I know k is some multiple of that divisor, D, that greatest common divisor, D. This implies that if I consider a to the k power, this is going to be the same thing as a to the d times r, or a times d to the r power, which means that this has got to be something in the set a to the GCD of n and k, which we're representing as little d. So we get the set of all elements generated by a to the k power has got to be a subset of all elements a to the GCD generated by a to the GCD of n and k. If I want to show that subset the other way, by the GCD theorem, there exists an S and a T in the integers such that a times s, actually, we'll do n times s plus a times t is going to be equal to their greatest common divisor, e. And what this does is it gives me a way to rewrite a to the d power. I can rewrite a to the d power as a to the n times s plus a times t. And I just apply some of those little rewriting tricks that we've done in a couple of these other proofs. I can separate this as two different multiplications. A to the n times s and a to the k times t, which is a to the n power to the s times a to the k power raised to the t. I didn't restate it in the proof just because I'm trying to go fast, but that n was the order of my element a. And then a to the n powers is going to become my element. The identity. This is the identity to the s power times a to the k to the t power, but this just boils down to then a to the k to the t, which is going to be an element of the set that is generated by taking a to the k and raising it to some power. Yeah, it's weird, but it's true. Therefore, we get anything that is generated by a to the d has to be included in anything that is generated by a to the k power. So we have now shown that they are subsets of each other. Therefore, a to the k power, that set that is generated by it, is equal to the set generated by a to the GCD of n choose k. And I'm already well over, so what I'll tell you is a corollary to this theorem is what gives us that result that we talked about in end of class on Wednesday. If we're considering Zn, we can get a generator for it as long as that value in the GCD of n is 1. What follows from this rate. But you just want to finish just a tiny bit. So that's it. So I'll leave it up for a second. It's late on a Friday, but thank y'all for sticking with me. If you have any questions for me, feel free to stick around and ask them. Otherwise, get out of here and enjoy your weekend.
I'll need to tell us more about them in time.
Okay, have a good one.
You too. You want good news or bad news? First, at the midterm. Bad news
Midterm,
about the midterm, yeah.
the Friday test.
That's a week from today. You want good news first or bad news
Bad.
first? Bad news? I won't be here next Friday. I'm really so disappointed hearing that. But I won't be here. So, what's the good news? Yeah, that's gonna be take home. Next Friday, okay? So you still have a test, it's gonna be, the way I do take homes, I'm gonna say it will be open at a particular time and closed at a particular time. You download the PDF off Blackboard. Write your answers or write the questions on your own paper, answer them, and then upload a copy of your solution. It's just like kind of what you've been doing with the whole plan. And you'll have to upload it by a certain time. All of that will be outlined very well in Blackboard. And so don't be too disappointed.
Studied as well, it should take like what, 2 minutes?
Yeah, it shouldn't take you more. But Sanaya, you want to hear one other good piece of information? Now think about it. Forgot I had to change my flight, so I actually have to leave Wednesday afternoon, so we won't have class on Wednesday either. What you're gonna be doing next Wednesday for this class is just studying for the test. Not sure if that's gonna help you out with any other classes, but just give you that little warning.
Okay.
Yep. Stop recording.